Hi, this is part 3 in our series on the turbojet engine construction. In part 1, we went through the structure that supports the turbojet engine test stand. In part 2, we went through the fuel delivery system and fuel choices. Today, we're going to get into the lubrication and cooling as well as the instrumentation. Now, this turbocharger on the table right here is an exact duplicate of the turbocharger that is used to construct the engine that we've demonstrated in the previous videos. And like all turbochargers, these things will last for thousands and thousands of hours, and all they ask from you is a reliable source of clean, flowing oil. The oil does a couple of things. It protects the bearings by lubricating them, but it also cools the bearings. The turbine housing here under high load can get so hot it can literally glow, and that heat can soak into the center section where the bearings are and damage them. So the oil is taking away some of that heat and protecting those bearings. And with a few very rare and extremely expensive exceptions, all turbochargers need that supply of oil. It doesn't matter whether they're using a sleeve bearing like this, or a ball bearing, a ceramic bearing, dual ball bearings, it doesn't matter. They all need that supply of oil. Now, the amount of oil that you need to flow is not very large, tens to hundreds of cc's per minute. And because the resistance in the housing to flow is relatively low, you don't need much pressure to deliver that supply of oil. If you go on a lot of forums or channels about performance engines and the use of turbochargers, there is often an obsession about trying to get the drainage of the oil that comes out of the turbocharger after it's done its thing as free as possible. The oil supply line that drains the turbocharger is supposed to be huge in diameter, very short, allowing the oil to just literally drip out of the turbocharger into the sump and under as low a back pressure as possible. That isn't really necessary in our application, and I'll explain to you why. The turbine undergoes substantial loading and temperature shifts. The turbocharger itself can spin up to 150,000 RPM, and it has to operate from temperatures below freezing to hundreds of degrees Celsius. And there are significant loadings that occur when this thing is spooling up. And so the seals on the edges of the bearing that keep the oil in the center housing have to have some tolerance to them, and therefore they all leak. And so if you have a substantial amount of pressure inside of that housing to deliver that oil flow, that pressure can overcome those seals and deliver oil into the input to your engine as well as to the output into your turbine. It can foul your fuel, it can create smoke, not such a good thing. That's why they want as low a head of pressure as possible. In our case, we have to remember that when the turbocharger is operating, that leakage can go in both directions. The oil can leak out, but the air and the gas can leak in. It can go either way, and it just depends on the differential pressure. When we're under boost, if the pressure inside the housing is low, that gas can get into the bearing housing and actually displace the oil and deprive the bearings of the protective lubrication. So we want to make sure that the pressure inside of the housing is at least as great as the pressure that we're creating inside the turbojet engine, and that's why we want a decent head of pressure. Now, the other thing that you will see here is, in addition to the oil output, the oil input, there are two additional fittings here and here. Not all turbochargers have these. These are water cooling fittings. In our application with a turbojet engine, we really don't need to use these. We could plug these up. The reason they're incorporated in some turbochargers is if you imagine you're driving this thing under high load, you're racing or it's a hot day, this thing will get very, very hot. And as soon as you park, stop the engine, turn off the oil delivery pump, the heat that soaks from this very hot turbine can get into the center section and cook your oil. It can damage your bearings. And so in smaller engines, what they often have is an electrically powered water pump that continues to circulate water through your hot engine block as well as through the turbocharger. This can remove the heat and protect the oil under applications where you've shut the engine off. In our case, we don't need to do that. We can keep the oil flowing after we turn off the engine as long as we want. So if you want to simplify the operation, lower the weight for a mobile application, you can simply plug up the water housing or the water connections if they exist in your turbocharger. I use them in our application, as you'll see, simply because they provide additional cooling to the turbocharger so that when we're done with an experimental run, this will help to pull heat away, cool off the housing, and just makes it faster for us to get into working with the engine. So now let me show you how these things work on the actual engine. Let's go outside. All right, let's start out with the water cooling system because it's the simplest. Over here we have a reservoir of some distilled water with some antifreeze in it, simply because we store this engine in a garage that can go below freezing and we don't want to damage the turbine housing with ice. This liquid is drawn out through the silicone tubing into this AEM pump, the same methanol water pump that we use for the fuel systems. The water that's pulled through here is then sent up through this tubing up to the engine above, and then it returns from the water cooling loop up here down to this radiator here, where there is an axial fan on the back that distributes and gets rid of the excess heat. And then the liquid simply flows back into the reservoir. There's no flow control, it's simply on, off whenever we turn the engine on. And the reason for the reservoir, it just makes up for expansion, contraction, and any evaporation or any potential leakage, although we haven't had any. That's why you want a little bit of extra volume here to be able to pull the liquid from here. Interesting thing about the radiator is it's actually from an industrial laser. We do a lot of laser work, laser experiments, and when we buy surplus or old lasers, sometimes they're not salvageable. And so what we do is we tear them apart and we pull a lot of equipment off of them. And they've got some really nice equipment, optics, small radiators, pumps, power supplies, kind of nice stuff to have around. Now, let's talk about the oil system. Pretty similar, but a little more complicated. Here we have the oil reservoir. This is about 2/3 of the way filled with oil. You do not need to use a jet engine turbine oil for this because, let's face it, this is an automotive turbocharger. So we use automotive oil. 10W40, 5W30, it doesn't matter what you use as long as it's compatible with the engine that this thing would be mounted on. The oil that's stored in here can be added as well as vented from this cap. When we operate the engine, there will be some gas that gets into it. It's kind of unavoidable. And so you'll get a little bit of misting and a little bit of vapor, and you want to be able to decompress the system without getting mist all over the place. So to have a loose cap on top is important. From the bottom of this aluminum container, there is a small tube that comes out the bottom of this connection, right at the bottom of the reservoir. Let me turn this around. Hopefully you can see this T a little bit better here, but the T comes out and the liquid oil is able to flow through this T and back to the back side of the support over here. These wheels are really nice. The oil is then drawn up here through a motorcycle radiator with a few axial fans on the back here to distribute the heat. And then the oil flows here into this oil pump. Now this particular pump from TurboWorks, W-E-R-X, is a super high-end pump that we used when we were doing some high-end offshore marine engine builds, and we're not using it now. It's been repurposed. It's very expensive. It's a few $100s and it's overkill. You don't need that kind of a pump. Any type of gear oil pump that you can get from a speed shop like Summit or Amazon, $20, $30, $40 will provide plenty of pressure and plenty of volume flow to pump the oil out into the oil filter. This is a 12-volt pump. You want to try to stay with 12-volt equipment simply because if you want a mobile application as opposed to what we're doing, it's always good to work with 12 volts when possible. The oil then is sent through this oil filter and then goes to the front of the support here. I knew eventually I would catch this cord. Now the oil from the oil filter then goes into this small manifold here. There is a valve and then a tube that leads back to the oil reservoir system to complete the loop, to allow the oil to continue to flow. The purpose of this valve is it restricts return flow, so that as we close this valve, we increase the pressure head above this upstream to deliver additional pressure to the tube that goes up to the turbocharger and then eventually down back from the turbocharger to the reservoir. One of the nice things about this clear translucent tubing is that you can see oil flow. So we're not just dependent on oil pressure, but we can actually visually see the occasional bubble that will flow through here to give us some feedback, knowing that we're getting some oil delivery. Now, I'm going to turn on the power supply here, and the power supply that we use to run all of the gauges and all of the pumps is 12 volts, but we're using line current to supply it. So inside of this rack mount case is a 12 volt DC power supply. When I hit this switch over here, we're going to send 12 volts to all of the gauges. This will activate the gauges, but doesn't turn on any of the pumps. We're using glow shift meters. You can get them from any kind of a company that you want, but I do like these. They work pretty well, and they provide a variety of different types of measurements that you can use them for. Just cutting a hole in the front of the rack mount, you can easily put these things in. They're easy to mount because they're made to mount in a dashboard, so they're really nice to work with. Now, what I'm going to do is I'm going to turn on the pumps, and you will see this little meniscus. I don't know if you can see it right now, but there's some air that has leaked into the system. And as soon as I turn the pump on, you'll hear the pump run, but you will also see this flow of liquid going up. Again, the visual feedback that you get when you operate the system. So here we go. 1, 2, 3. And you can hear the pump working. Now, if you look down below, this gauge right here is the oil pressure, and it's being measured in this small little block that I've interposed between the manifold here and the output to the turbocharger. This is reading just a couple of PSI, sufficient obviously to flow oil through the system. You can see it dripping down here, little bubbles. I don't know if it'll show up very well on the camera, but I can see a couple of very small bubbles flowing down here, and you certainly saw the oil going up here. As I close this valve, you'll see the pressure increase here because we're restricting the return flow, and that's what I do just before a run. See the pressure gauge going up? Like that, and back down. So I keep this wide open just to give me flow, get rid of any air bubbles before we do a run. But when it's time to do a run, and I want that additional pressure so that we don't end up depriving the bearings of oil because of an inflow of gas, I'll turn this thing up, but I never turn it off. This other gauge over here is an oil temperature meter, and it turns out it doesn't work. I must have busted it at some point, either a high voltage spike, or I stepped on it, or I dropped it. I did something and I broke it. It doesn't work. The point is, though, you really don't need it. It's overkill. Even at full operation for a long period of time, this oil never really gets that hot. You can almost put your finger in it, maybe 40, 45 degrees Celsius. That's about all. So if you want to save some money and some space, you really don't need an oil temperature gauge with this kind of a setup. But oil pressure, that's critical. Now, another thing that you'll see here is the turbine inlet temperature. This little probe that's sticking up above here at the output of the combustion chamber and the input to the turbine housing is measuring the temperature of the exhaust gases that are surrounding the turbine inlet temperature. Now, in professional big-scale Rolls-Royce General Electric engines, they tend not to measure the pressure or the temperature right there because they have very advanced metallurgy and they have very sophisticated turbines, and they can run at temperatures that will generally destroy most thermocouples. So what they will do is they will measure the exhaust gas temperature after the turbines, after it's cooled off a bit, and then use their multi-million-dollar modeling programs to determine what must have been the temperature of the gas going into the turbine. We don't have that problem. Even at full operational temperature, we never really go above about 900 degrees Fahrenheit into the turbine. And so this thermocouple can handle almost twice that temperature. So we just go ahead and directly measure the temperature of the turbine inlet gases. And that helps us to protect the turbines, because in these cheap Chinese turbos, which is what these things are, the maximum continuous operating temperature for the turbine blades is about 1200 degrees Fahrenheit. And for you metric people, please forgive me, because I'm going to be giving a lot of numbers, and it's very hard when I have to keep giving you dual numbers. You'll have to do a little bit of interpretation here. Nevertheless, 1200 degrees Fahrenheit sustained temperature. In the more advanced turbochargers from Garrett, Borg, Warner, Precision Turbo, they have better metallurgy, and they can allow the turbine blades to go several hundred degrees hotter, which means higher performance, higher thrust, but much more expensive turbochargers. So in our case, 900 degrees is plenty. It actually gives us a fair amount of headroom, because when we add the compound turbocharging, we're going to be getting higher temperatures in here, so we want that additional headroom. The final gauge over here is the pressure, or the chamber pressure. This is measured by this little fitting here at the output of the scroll of the compressor. And what this measures is PSI gauge, or PSIG. And this is an important thing to be aware of. I'm going to turn this guy off for now. This is an important thing to be aware of whenever you're using gauges and you're dealing with pressures like in a turbocharger or turbojet. There's PSI-A absolute and PSI gauge, which is a relative pressure. All of these gauges here are reading gauge. It's a net pressure. So when they read 0, what they're really reading is 1 atmosphere. So when you go to 14.7 PSI gauge, you're actually going to about 30 PSI absolute. When we bring this turbocharger up to about 25 PSI gauge, we're actually bringing it to about 40 PSI absolute. And so 14.7 PSI atmospheric and about 40 PSI absolute. We have a compression ratio inside of our turbocharger of almost 3-to-1. And that's about as high as you want to go with a single stage turbo. If you look at the turbo maps, you look at the performance of turbochargers, and it doesn't matter whether they're expensive or cheap. They basically follow pretty much the same sort of maps. Once you get to about a 3-to-1 compression ratio, you can't get much higher with a single stage. If you try to do that, you're mostly adding heat because they become very inefficient. If you want to go to higher pressures, you need to add a second stage turbocharger. An interesting thing about the Allison 250 engines that I mentioned in a previous video, the axial turbines that these things use, they use a combined axial and centrifugal compressor, is that the axial compressor stages do not compress as much per stage as a centrifugal compressor, but they handle much higher volumes. So the input to the 250 engine has several stages of axial compression to compress the air moderately, but reduce its volume. Then they take that reduced volume at a higher pressure, and then they double or triple it in a single final centrifugal compressor stage to get up to the high 9 to 10 to 11 compression ratios of the Allison 250 engines. Interesting thing. Now, the final little meter you see here is a pulse counter. What that does is it allows you to measure the speed of the turbocharger. Directly trying to measure the speed by putting something onto the shaft when this thing is spinning at 150,000 RPM is almost impossible. And so you do it indirectly. This is a Borg-Warner Hall sensor, Hall effect sensor. Effectively what happens is right near the tip of this sensor, if you place a conductive material, like say the metal blade of a compressor wheel, and you get it to within about 1 millimeter as it passes in front, it will produce a small electrical pulse, which is sent down the line to the pulse counter. If you then count the number of blades in your compressor, let's say it's 7, you can enter in a divisor, and so this will calculate not pulses per second, but RPS, or revolutions per second, or if you want, revolutions per minute. This is pretty important to do if you're getting your turbocharger up to pretty high performance levels, or you really want to tweak the most you can get from them. Using a Hall sensor is the way to do it. Now in the high-end turbochargers, again from Precision Turbo or Garrett, they actually make the compressor blocks here with a small segment that has a machined face that allows these little probes to be inserted directly in, to be within about 1 millimeter of the blades. You don't want to be any closer or any farther, and at the right angle to hold them securely in position. These cheap Chinese turbos don't have that. So when we get to the compound turbocharging, I'm going to need to weld or put some sort of a block and machine something to support the Hall sensor so that we can effectively use the pulse counter. And that's pretty much it for the setup. Simply said, you don't need to measure the oil temperature. You do need to measure the oil pressure, and you need to be able to control it. You want to know what the turbine inlet temperature is, and you want to know what your boost pressure is in order to determine performance. It's nice to do everything at 12 volts because then when you want to get this thing off of a cart and away from the house, you're not looking at voltage converters. You can just simply use a battery to supply all the needs that you have. In the next video, we're going to get into the starting system and the ignition system. So hopefully you found this interesting, and we'll be talking to you soon, but we'll finish this up with some pretty interesting demonstrations. You take care, and we'll see you soon.